Welcome to Hot Chips 24. Session 6, Technology and Scalability.
This is Session 6, Technology and Scalability. I'm Forrest Baskett. I'm your session chairman. The first talk is Floating Point Processing using FPGAs by Michael Parker. Michael is responsible for Altera's digital signal processing product planning, including variable precision FPGA silicon architectures for DSP applications, DSP tool development, floating point design flows, DSP IP and video IP. Joined Altera in January of 2007. He has over 20 years of DSP wireless engineering design experience with Alvarion, Soma, Avicon, TCSI, Stanford Telecom, and several startup companies. As an MSCE from Santa Clara University, a BSCE from RPI. He's authored a book entitled Digital Signal Processing 101, and in 2010, has 30 technical articles on DSP, radar, floating point, and various other technical subjects. He's got another book on video and image processing to be published shortly. Michael?
Thank you, Forrest. Good morning. As the title says, I'm going to be speaking about floating point processing on FPGAs. Most people, when they think about FPGAs, they associate that with fixed point processing. That's where 99.9% of the revenue of the FPGA companies come from, and that's what we're accustomed to thinking about. FPGAs do offer floating point functions, but they've been almost like toys up until now. You could do a sine function or a trig function and maybe build just a small little circuit that would run in floating point. But if you tried to really build a large-scale floating point circuit, the compromises were totally unacceptable. It used excessive logic, it ran very poorly, and so people kind of have this impression that floating point and FPGAs just don't mix. So actually that's no longer true, and so what I want to do is go through some of the more recent results, and what I'm going to do is talk a little bit about the silicon architecture and some of the things that enable that. But the key thing is really there needs to be a new design approach taken to make floating point work on FPGAs. FPGAs are really designed for fixed points, so certain things need to be done to make floating point work efficiently. Because this is kind of new, there's naturally going to be a lot of skepticism, so I actually want to show a lot of real-world results and give you guys the performance, the GFLOPs per watt on several popular algorithms. And these will be, real results. They're not going to be marketing numbers. So we always hear, the different manufacturers are always quoting their peak performance and X number of teraflops and things like that. We can quote those as well, but what I'd really rather get down to is what's, realistically possible and what you're going to see if you decide to use an FPGA to do some of your floating point algorithms. I'm also going to have a little bit of discussion on the computational accuracy. And then also, there's been some benchmarking by a third-party Berkeley design technology on this flow and on some of these algorithms. So to begin with, I'm going to talk briefly about the actual FPGA silicon architecture. So I'm going to be referencing Stratix 5. That's Altera's 28-nanometer FPGA architecture. These devices started shipping early last year. So if we go ahead and we look at what's new, the biggest innovation in terms of floating point has occurred in the hardened DSP blocks in the Stratix 5 FPGAs. So these are called variable precision blocks, and the reason is that these blocks can be programmed for different levels of multiplier precision. So when you think of FPGAs, they're configurable logic. The logic you can change to whatever you want. The memory sizes can be whatever size you need within reason. You can kind of build your own thing. But the multipliers have been kind of constrained to be at a fixed precision. So with Altera, that's no longer true. You can dial in the precision you need. Now, for floating point, what you find is you really need symmetric size multipliers. Having an asymmetric size multiplier doesn't do you any good. That may be good for maybe a fixed point FFT, but most applications, symmetric works better. So with Altera, the key sizes that really work well for floating point is going to be the 27 by 27 and the 54 by 54 modes. So if we look at 28 nanometer, it's not just the architecture, but the densities that help. So kind of comparing where we are at 65, and then there was a modest increase going to 40 nanometers, but at 28 nanometers, you see a really large jump in densities. And especially if you note the light blue column, that would correspond to single precision floating point. There was a 6x increase in the density in these devices. So it really makes it possible to go after large algorithms from a hardware point of view. The resources are there. But that's not enough. You can have the resources there, but when you go and you try and build them using floating point adders or floating point multiplier megafunctions or sine or cosine megafunctions that you can pull out of the libraries from the FPGA vendors, and you start to string 100 of these things together, the whole thing breaks down and you really get poor results. So what Altera did was they took a different approach, and we call this fused data path. And what we're trying to do here is to take an algorithm and look at it across the whole algorithm, not look at it from each and every atomic operation. So if you think about the way things are done in the processors that have been discussed so far in the conference, whether it's from Intel, AMD, Nvidia, and so forth, the IEEE compliance is basically at an atomic level. And so you have IEEE numbers coming in and IEEE numbers going out at basically the adder level or the multiplier level. The problem with that for FPGAs is it's an ugly hardware format. So you have this implicit 1 in there. It's not 2's complement. You have to normalize and denormalize each and every operation. And so when you try and replicate this capability in the FPGA, you just wind up with a real mess. What happens in particular is with the normalization and denormalizations, these use a lot of routing resources. So you don't even necessarily see it from a logic point of view, but the routing density in today's FPGAs is just not sufficient to do this normalization and denormalization for each add and multiply step in a big floating point circuit. So instead, Altera took an approach, and we have an automatic tool flow, which you input your algorithm, and it will fuse these things together. And internally, within the algorithm, we dispense with the IEEE representation because it just doesn't work. So instead, what we're using is we're using 2's complement numbers, number 1. The implicit 1 goes away. The sign bit is integrated into the number. And we don't normalize and denormalize every single operation. So right away, that's going to raise flags. Well, you're just cutting corners. This is just going to hurt the precision. But because it's an FPGA, we have capability, we have flexibility on how wide the mantissa is going to be. And so what we do is we actually extend the mantissa width, and then we don't normalize and denormalize each and every operation. And as I'll show later in the results, that's going to actually give you superior precision than you get with IEEE. It really works on a large-scale algorithm. So maybe a quick way to think about this is a vector dot product, where you have a series of multipliers, and then you're summing together those products. This is key to a lot of the matrix algorithms. So what you could do is you could do this normalize, denormalize every single one of these operations, but imagine if you had a tool that looked at these things and you did your denormalization, say where it's shown here, right after the output of the multipliers, and then you did a 2's complement adder, and then you normalized at the end. So this could be considered maybe a very low-level block floating point inserted in your circuit. If you go ahead and you extend your mantissa width, you're actually not going to lose any precision, because sooner or later, the number with the largest mantissa is going to determine that exponent at the end. I'm sorry, with the largest exponent is going to drive the exponent of the final result. Now, normally you don't want to go ahead and do this truncation early. You would want to wait to the end, and when that result actually merges in. Here we go ahead, by the denormalization, we're using the largest exponent right at the beginning, but by carrying extra mantissa bits, we more than compensate for that. And of course, we have a whole bunch of functions which you can drop in, and within these functions, for instance, a sine function, or an arctan function, or an inverse square root, the same process is applied. So I want to go ahead and start looking at some of the actual results here. I'm going to start with the most ubiquitous, which is an FFT. And the device that I'm going to be looking at is going to be kind of right in the middle of the Stratix 5 line. It's the mid-sized device in our GS family, which is more oriented towards DSP applications. And so that device has on the order of about 3,000 multipliers. It's about 460,000 logic elements. So looking at this result here, one thing I want to point out is that the device is pretty full. There's 14 single precision 1024-point FFT cores. So it's using on the order of 90% of the logic. So that's considered pretty full for an FPGA. And the device is routing and closing timing at 300 megahertz. That's pretty impressive just for a fixed point design to close timing at 300 megahertz on a 90% full large FPGA. So it kind of proves that this approach works, and it's using the routing resources at a sustainable level that you can actually close timing on a device full of floating point. And so I think this is the first time, this is the first approach that's allowed large-scale floating point to be used in FPGAs. We could compare this, for example, to a leading Texas Instruments DSP. TI has added floating point to their most recent high-end DSPs. And so what I've done here is I've compared a large FPGA, it's a D8, with the most powerful TI DSP. The TI DSP has 8 cores. In this large FPGA, we can fit 20 of our FFT cores. And by comparing the aggregate result, you can see that you're getting about 8 times the throughput in the FPGA on single precision floating point FFTs. I want to skip next to another algorithm, which is Cholesky decomposition. I don't want to go through the details of this algorithm. We don't have time for that. But what I want to kind of point out is this is a very commonly used algorithm in a lot of applications in military. It's used in medical imaging, some financial applications. And it involves basically matrix inversion, solving the problem where you need an equivalent of a matrix inversion on conjugate symmetric matrices. And so what goes on here is, don't worry too much about the equations, but what I want to point out is you need a vector dot product. That's where over 90% of your floating point computations are going at. So if you look at underneath this square root, you see a sum of multiplies going on there, which is a vector dot product. So you can imagine if you have a 100 by 100 matrix, you're going to have vector dot products up to 100 wide. You're going to also need things like square root, inverse square root, things like that. But well over 90% of the resources are going to be in that vector dot product. So it's really important to do that efficiently. The other thing that goes on here is that there's a lot of recursion. So here in the off-diagonal elements, you can see that you're using the on-diagonal elements are being fed back in. So there has to be an efficient way to manage this latency of these huge dot product computations and then feed those back around and use them recursively. One of the key things to getting efficient throughput and getting high flops is to go ahead and keep those computational engines busy every single clock cycle. So when you have a lot of recursion, that can be a challenge. Then there's another operation called forward substitution that's needed to be done. Again, that uses a very similar equation structure, and it's the vector dot product that's the key operation. That's where all the floating point operations are. And then there's yet another one known as back substitution. Again, vector dot product. And so this is kind of what the block diagram of this looks like. And it's a parameterizable core that's been built with these tools, and people can go ahead and specify the size of their matrices and go ahead and the core will just be built and run. So I've got some results to show you guys. If we look at this, I just picked different sizes from 30 by 30 up to 400 by 400. The vector size you see is how wide the processing is in terms of how parallel it is. So if it's a 30 wide vector size, that means you have vector dot products of 30 wide. It's dealing with 30 elements at once in a row of the matrix. You know, with 400, it's been split up into 100, so there's actually 4 passes for each row. So if we go ahead and look at this, you can see the GFLOPs given on the right-hand column, and you can also see the FPGA resources in the middle. Notice that only about, in worst case, about a quarter of the DSP resources are actually being used. So this tells you that if you did an algorithm that was very simple, like just doing matrix multiplies, you could get a lot higher flops if you're going for a marketing number. But here on a real-world algorithm, you're seeing that the FPGA's hitting on the order of 100 GFLOPs. And what we can also do is this was run on an actual FPGA development kit board, and then we could get the GFLOPs per watt. So the GFLOPs per watt is coming in the 5 to 6 GFLOPs per watt. Again, you know, when you fill up the device, you get better numbers because you do have that large static power contribution. So if you have a very small design, you're still going to pay that penalty. So these results are available. The other thing I wanted to point out is look at the throughput here. So with the small matrices, you're getting throughput on the order of 500,000 matrices per second. But the computational complexity goes up with the third order of the matrix size. So you can see when you start to get large matrices, you're down on the order of 1,000 or 1,200 matrices per second. So I wanted to show some NVIDIA results. These are taken from published papers. So the NVIDIA results don't go with the smaller size matrices that we're seeing up here. They're horribly inefficient at small size matrices. So the published results that I could find, basically the smallest I could find was 512 by 512. So by comparison, here's a part that's rated at almost a teraflop, but what you're getting, depending on which library you use, is between 20 and 60 GFLOPs on this 512 by 512. As the matrix size gets larger, the NVIDIA GPU starts to become more efficient. It's easier to manage the latencies and to spread the large matrix processing across the high number of cores. With the small size matrices, that's more challenging. Here's another result with a very similar algorithm, which is the LU decomposition. It's another matrix algorithm, and you can see similar kinds of results. You're in the 50 sort of GFLOPs range for 1,000 by 1,000, and then it gets better as you go to the larger matrices. And this is with a fairly current NVIDIA. This is the C2050. Again, these are published results. The papers they came from are listed here if anybody wants more information. Another algorithm is QR decomposition. It's another matrix algorithm. It's very popular in military applications. It's getting a lot of use in wireless for MIMO applications. And again, it's a complicated algorithm. It's recursive. You need to use floating point. It's very difficult to do these things in fixed point. This algorithm, again, we're not going to go through it at all, but it does need the vector dot product. That's where over 90% of your computations are going to sit. So if we go ahead and just take a look at this, there's a couple different steps in it that are implemented in the core. And here's, again, the resources. So what we have here is a QR decomposition can work on rectangular size matrices. So if you have an overdetermined system of equations, you'll have more equations than unknowns. That's going to result in trying to solve a rectangular matrix. So here's a few different sizes that were entered into this core, and you can go ahead and see the vector size, and you can see the GFLOPs that were involved. So again, for large matrices, say 400 by 400, you're hitting just over 100 GFLOPs. And similarly, I've got the results showing the power used in the FPGA. And so here you're seeing the QR decomposition is not quite as efficient of an algorithm, so your GFLOPs per watt is a little bit lower. You're more on the order of around 4 GFLOPs per watt versus the 5 to 6 that you saw in the Cholesky. And again, the flops used on these are taken from the theoretical number of calculations to implement this algorithm. The flops isn't coming from looking at how many multipliers were there and how fast they're running and so forth. It has nothing to do with the implementation. It has to do with, in theory, you can go ahead and calculate exactly what floating point operations are required to complete this algorithm, and then we go ahead and look at what the performance of the FPGA is. So that way you can compare on these algorithms to different architectures, whether it's a GPU, whether it's a CPU or an FPGA, because the flops required for a given algorithm is the same on all of these, no matter how they manage to implement them. And if they implement them inefficiently, they're just going to show poorer numbers. So just talking a little bit about some of the accuracy and precision that you get. Again, this is, we do deal with IEEE numbers going into the core and coming out of the core, but within the core, we don't use the IEEE representation. So that's naturally a concern for people, and there needs to be a way of verifying what is the true accuracy you're getting out of these algorithms, and is it sufficient, or are you, getting good results, but at the expense of cutting corners. So here is the analysis on the QR. There's a similar one on the Cholesky. But what we did was we went ahead and computed this in MATLAB, which is running on a desktop PC, so that's going to, of course, be IEEE compliant. And we compared those results to the actual results. Because we're doing matrix inversion, we know we can back calculate, know what we started from. We know the precise level of error. So you're going to see errors when you run this in MATLAB. So why is that? It has to do with an IEEE floating point. You're going to go ahead and you're going to have rounding throughout. So you're going to have rounding. You're going to have, there's non-associativity of some of the operations. So in floating points, you never get a bit exact result the way you're used to in fixed point. So there's always some level of error. So what we're showing here is that the RTL generated by the DSP Builder tool flow is actually giving slightly lower levels of error than the MATLAB approach does. And so that's confirming the integrity of this design flow, that you're not giving anything up to take this approach. Now, even on a GPU, for example, you're going to get different results than you're going to get on an IEEE compliant CPU. And that's because when you change the order of operations in floating point, you get different results as well. So that's something that people need to kind of come to terms to, that the only way to get results precisely matching what you get on a particular CPU is to always use that CPU for computing. When you go to a different architecture, whether it's FPGA, GPU, or whatever, you will get different results. So kind of as a summary is that high-performance floating point is now really feasible in FPGAs. The IP is there, the devices are there. This can work very well in many applications. As we saw, the FPGAs work really well on smaller size matrices, and that can be very useful in a lot of applications such as military and wireless. Now, if you're doing, say, climate modeling and you're dealing with matrices that are, 10,000 by 10,000, then a GPU may be a better choice. So it really depends on what you're doing. Different architectures may have different advantages. Where the FPGAs are going to tend to be used is where very low power consumption is important, where very low latency is important, and where you have smaller data sets you're dealing with. For example, this tool flow and one of these FPGAs was recently used in a missile system where the radar had to be completely integrated into the cone of that missile. And it was a small missile that's used for short ranges. You couldn't put a CPU in there. You couldn't have a ground-based system doing it. It had to be mounted inside there. So for these kind of applications, the FPGA was really the only solution possible. I've actually had some discussions with some people on the military side, and they're looking at new algorithms where they need to have on the order of 100 teraflops worth of processing power airborne in an aircraft. It's pretty hard for them to imagine how they're going to do that using CPUs or CPUs and GPU combinations. So they're really looking at ways, are there new architectures that are more hardware-based? Maybe they aren't quite as flexible as a GPU or a CPU, but they can allow you to get much higher throughput, higher computational rates, and better GFLOPs per watt. Because this is kind of new, I've really made an effort to kind of present real-world benchmarks to you guys, not a lot of marketing numbers. The one thing I do want to say from the marketing point of view is that Altera is developing OpenCL for FPGAs. So that's in the hand of a few beta customers right now. It's going to be announced in a couple of months and released early next year. So that's going to make it a lot easier for people to go ahead and compare performance across different CPU and GPU architectures against FPGAs, because they'll be able to use a common language, and you won't have to be an FPGA programmer in order to access an FPGA to use for these type of floating point operations. And then lastly, I'd like to say is that at Altera, we see floating point is really a big part of the future. Fixed point is going to be with us for a long time, but as we start to go towards higher level synthesis, languages that allow you to get out of programming in VHDL and Verilog, floating point really provides a lot of productivity benefits and really facilitates going to C-type language flows or other type of ways to do design entry. So as we continue down this path, you'll see that the kind of the floating point penalty is going to continue to decrease. And at some point, you'll get to, so there's virtually no penalty to do floating point versus doing fixed point. Right now, in the results that we're showing here, the floating point is using considerably more logic than it would take to implement something in fixed point. And the algorithms I've chosen are ones that you almost need to do in floating point. But at that point, we expect that a lot of users are going to begin to transition over to floating point because it's not going to cost them much. And then just the productivity benefits, not having to worry about fixed point issues, is going to really come in handy. So with that, I'm open to any questions that people may have.
So first, let's thank Michael for the talk. So questions? Here's one right here.
Satoshi Matsushita, NEC. I have two questions. First one is how do you handle the floating exceptions like divide by zero? And the second one is about not a number or the infinity or such kind of special numbers.
Okay, so currently our tool flow does not allow denormalized numbers. So the numbers that you input into the algorithms or into the cores have to be valid IEEE representation. So, but of course, even if you do that, going through an algorithm, you can wind up with things that are not a numbers or exceptions. So those will be converted into NAN number representation, and they will be passed out at the other end of the core. At the current representation of the tools available today, we don't actually bring out the exception flags. That's something that'll be happening at a future release. It may not be as important because, again, you can't have interrupt vectors or things like that respond to this. Unlike a processor, when FPGAs are normally used, you're going to have something that's very real-time, and what you really want to know is, did you get an invalid computation? You don't have time to go back and redo anything. So being able to send out NAN numbers when these type of things occurs is sufficient for the customers we've been working with.
So when a division by zero occurs, we are noticed by the infinity, right?
It will actually output an NAN number when a division,
okay,
when that happens.
Over here.
James Tringali from Rambus Labs. You mentioned in your examples were more embedded applications. I'm wondering if you're getting any interest from the HPC community, especially with respect to the challenge that's been put out by the DOE for them to hit a certain power level for the exaflop generation.
We are getting a lot of interest from those guys, from them as well, Department of Energy, but also from the financial guys. Like we had a presentation yesterday talking about the high-frequency traders and how trying to get their computations as quick as possible. Aside from just raw number of flops, FPGAs tend to do really well on latency. you can get the data in, you can get it out, and it's typically very low latency. We don't have off-chip memory that we have to store everything in. So there's a big market out there for FPGAs, and both single and double precision is being used for those.
Thank you.
Over here.
I see the size of the matrices that you have and the gigaflops and the gigaflops per watt. You haven't said too much about how you get the samples in and out. The IEEE 754 typically comes from a CPU or a GPU. And are you using SerDes? And what are the rates for these examples you've given, specifically the sample rates?
So these benchmarks are using cores that you would drop into the FPGA design. So we were actually generating the data on chip. We had random number generators that were generating these matrices and passing it in. Of course, you can drop in a PCIe core or a gig Ethernet core or things like that. But in generating these type of benchmarks, we weren't trying to address all the I/O issues. We were
Can
just
you say for 1,000 by 1,000 matrix of floats, what kind of I/O would be speeds are required to keep up with the gigaflops you've listed?
Off the top of my head, I can't, but the larger size you go, the easier it gets. Because you need more computations for a given amount of data coming in. It's actually more challenging for smaller matrices.
Right. Thank you.
Okay, one more. We're running out of time.
Liang Kai Wei, I'm from Qualcomm. So yeah, when someone says they're IEEE compliant, I always have questions. So how compliant is that? So do you have a fuse multiplier add that it's actually regulated in the IEEE 754? And also, by the way, the IEEE, the standard doesn't actually regulate the precision for the duct product. That's kind of the reason why there's errors there. So that's kind of the other comment I have. So do you have FMA? Basically?
Yeah, so no, we don't have, like the way you hear about, like Nvidia has FMA. They define FMA for a single multiplier and adder. We're doing this across the whole algorithm, and so it's going to actually be different depending on what your design is. Right. We're not IEEE compliant within your algorithm. We're IEEE compliant in terms of the representation of the inputs and the outputs, and that's why we provide the ability to do this analysis to show what your level of errors are.
Okay.
So you can be sure that you're getting good quality results.
Okay. All right.
Okay, let's thank Michael again.
Thank you.
So our next talk is an IA32 processor with a wide voltage operating range in 32 nanometer CMOS by Gregory Ruhl. Gregory received a BS in computer engineering and an MS in electrical and computer engineering from the Georgia Institute of Technology in 98 and 99 respectively. He joined Intel in Hillsboro in 99. Has published research in areas of high-performance computing, near-threshold voltage computing, low-power circuits, on-chip networks, memory, signaling, Ethernet hardware acceleration. Greg currently works in the Compute Component Development Organization, investigating new technologies and designing next-generation processors. Greg?
Thank you, Forrest. So very excited to be here and present our research. Before I get started, I'd like to thank all my fellow researchers who made this research possible. As Forrest mentioned, I'm going to present an IA32 processor with a wide voltage operating range in 32 nanometer CMOS. If the clicker works. So our name for this was Claremont. And so why did we do this research? Previous research has shown that NTV holds a lot of promise, but typically these are on smaller circuits, small experimental cells. We wanted to prove the efficacy of the technique on a full IA core. Additionally, we feel that wide dynamic operating range is a valuable technique, so being able to operate at NTV for certain application profiles is important, while also operating at Vmax for certain applications is important, particularly as we start to get into many core systems. And the third goal of the research was to actually come up with a CAD methodology to create this NTV and wide dynamic range core. So my agenda today, I'm going to go over some general design challenges for NTV. I'm going to discuss our Claremont prototype, And then I'm going to go over some of our specific design strategies and methodologies we used. And then I'm going to follow up with the results and a summary. So generic design challenges for NTV are reduced I-on, I-off ratios, which basically are going to increase your variability, hurt your noise margin, and that's going to result in circuit functional failures. Also, as the power performance profile differs, we become more sensitive to PVT variations. And some other issues are that the tools and methodologies that are currently out there are not very mature for extreme low voltage. So I'm not talking 500 millivolts, I'm talking 350, 400 millivolts operating. Wide dynamic range actually creates a whole additional set of challenges, such as device versus interconnectivity delay scaling. The interconnect scales at a different rate than the devices do. And also, when you're dealing with memories on one voltage and core on another, you have to cross various voltage domains. And so how can you handle that in an effective manner as voltage is changing? So now I'm going to discuss our Claremont prototype. Claremont is a P54C. It's an IA32 core. It's a legacy Pentium from 1994. This is a 32-bit CPU. It has a 64-bit data bus. It's a superscalar architecture with an in-order pipeline. The floating point unit is pipelined as well. There's a dynamic branch prediction unit. There's two caches. There's an I cache and a D cache, each 8 kilobyte in size. And finally, we have a fractional bus unit to talk to the front side bus. This became critical because as we scale our voltage or our frequency up, and as well as down, we needed to actually be able to communicate effectively with the motherboard. The motherboard's maximum frequency was 66 megahertz. So at Vmax, we may be at a couple hundred megahertz. We need to be able to scale the ratio. So before we actually started building this, we tried to set some design targets. This chart is showing a low VT process and a high VT process. As you can see, both are showing a normalized energy minima, and they are occurring at different points. So while low VT, the low VT obviously is going to consume more energy per cycle, and the high VT is going to consume less. The total gap between Vmax and the energy minima is about a 5x improvement. So this may be a review for most people. Obviously, lower voltage, better energy efficiency, down to a certain point, then the energy begins to increase as you drive the voltage even lower. So our Claremont prototype, this is a block diagram. Our goal here was aggressive voltage scaling. So you'll see there's two power planes. There's a memory plane, which is in kind of an orangish red color. And then there's the core plane, which is in green. Also between these domains are level shifters. So we have level shifters between the memory and the core. And we also have level shifters from the core to the front side bus. So our initial design goal was to hit below 20 milliwatts at 500 millivolts for the core, and also for a wide dynamic range. This meant we wanted functionality at 500, 750, and 1.05 volts. And a little bit more about this block diagram. There, you'll note the level shifters. We actually use 2 stages of level shifting between the memory and the logic, and 3 stages of level shifting from the core to the front side bus. People are familiar with the old Pentium. Remember that it's a 3.3 full swing bus. So nobody designs IOs like that anymore. So we actually had to level shift all the way up to 1.8 and then build a custom IO to swing at 3.3 volts. So another interesting feature that we added was a proactive power management into the floating point unit. This basically monitored the instructions in the floating point pipeline and would dynamically turn on and off the floating point unit based on activity. So if there's no instructions in the pipeline, turn it off. That's the simple explanation. However, we did make this threshold programmable, because if you would, the second that the pipeline is empty, if you were to turn off immediately, that may not be the optimal situation, because another instruction could come in right afterwards. We did have a single cycle wake up, but by constantly turning this on and off, you're actually burning more energy to power up the actual power plane, the capacitance of the power grid. So it's important to have that sleep threshold to be programmable, so then you can determine what the optimal setting would be for the best energy savings. So now I'm going to discuss some of our design strategies and methodologies specific to Claremont. So the near threshold voltage logic, we've presented the circuit details in other conferences, and I did include those slides in my backups. So I'm just going to go through these quickly. The first technique was we needed a variation-aware library pruning to ensure reliable NTV operation. What this meant was limiting the transistor stacks of the actual devices, so also eliminating transmission gate muxes, and also eliminating contention circuits. And when I talk about contention circuits here, I'm talking about non-sequential contention circuits. We also needed to prune any minimum-sized devices. Minimum-sized devices have extremely high variation. And also, we had to redesign our sequentials. So the sequentials worked down to a certain level, and what we ended up having to do was upsize our keepers, as well as make it fully interruptible with clocked inverters. For our register file, which is for the I cache and the D cache, we use a 10 transistor single-ended transmission gate register file cell topology. And we also actually increased the number of tracks that that cell occupied, physical metal tracks, which improved our noise margins. Also, our level shifters were semi-interruptible split output level shifters, and as I had mentioned on an earlier slide, we actually needed 2 of these to reliably operate between, say, 350 millivolts and 650, 700 millivolts on a memory. And then we actually used 3 of these to get up to 1.8 volts for the actual full swing I/O. The full swing I/O, that was a highly tunable, fully cascoded I/O design. It required special transistors, and one of the key challenges was, here's this, what is it, 17, 18-year-old motherboard. We needed to, with a lot of variation on the board, what voltage is that system controller actually expecting? What does it want, and what is it driving to us? It wasn't 3.3 is a spec, but believe me, we're running well outside of the spec range. So we needed a variety of different pull downs and pull ups of varying strengths. We needed various drive strengths, so this is a very highly tunable I/O. So low voltage timing convergence. As people may be aware, when you have random or systemic process variations, that's going to lead to uncertainty, and then you're going to have failures. So we have max failures and min failures. I'll discuss max first. Our max convergence strategy, so setup violations are not fatal. You can just dial down the clock frequency. And for research, that's usually fine. So the conservative library pruning, that enabled us to have a low variation impact and better correlation when we actually got to silicon. Another actual advantage of the P54C is that it's a very shallow pipeline. So having a lot of gates between your flip-flops gives you more averaging of those variations. So if you had a very deep pipeline or a low number of gates between sequentials, let's just say you had 10 gates, the probability that the majority of those were skewed in one direction is much higher, and so your variation could be a lot higher. So shallow pipeline is good for NTV. Our min convergence strategy, hold violations are obviously fatal, as people well know, so it's important to ensure sufficient hold margins. We use Tango for our timing roll-up tool, and so Tango by default does a typical data clock path variation penalty addition. So what we needed to do, though, we need to consider sequential hold variations as well, and I'm going to discuss those here. So bottom line, variation-aware timing convergence is important. So for hold margin, we used a Nova tool, and so here's an example of a simulation, pre-silicon simulation between a 1x and a 2x minimum size local clock inverter. You can see at 500 millivolts and 0 sigma, both have a negative hold time, which is good. At 5.5 sigma and 500 millivolts, we're still in the realm of acceptability. 686 isn't great, but it still would meet our actual phase requirements. However, at 400 millivolts, note that it really shoots up to about 9.9 nanoseconds, and that's basically fatal. So clearly, 1x local clock converters are out. So we had actually done a simulation for 1.5 to 2.5 and 1, and we decided that 2 represented the best cost to performance. So now some wide dynamic range design techniques. And I mentioned at the top of the talk, interconnect delay scaling is a major issue when you're doing these wide dynamic range chips. That's because interconnect does not scale and devices do. So at 500 millivolts, you'll see that our device delay accounts for 98% of the delay of the path, where interconnect is 2% of the delay. At 1.05 volts, device delay is 75%, and interconnect is 25%. And this is on a shallow pipeline. When you have an even deeper pipeline or less gates, you're going to need, typically we found that you're going to need longer routes, and that would exacerbate this problem. So the key takeaway here is that your synthesis flow needs to fully take into account the variation of the interconnect delay component. So now I'm going to go over some of our synthesis corner evaluations. We had attempted to run synthesis at 500, 750, as well as 1.05 volts. And this is going to show why we ended up using the low voltage corner for our synthesis target. As you can see, for both synthesis corners, when we do a timing roll-up at the 750 millivolt, our total negative slack is looking fine. However, when we get to 500 millivolts, total negative slack of the 750 millivolt synthesis corner case exceeds our actual timing margins. So again, we pick 500. So the problem here is that when you're at 750 millivolts, it's calculating a lot of this interconnect delay into your path. So that's setting a particular max timing path. But then as you reduce the voltage, that interconnect becomes negligible, and then all of a sudden you're down into a min violation situation. So it's important to prioritize these interconnect delay dominated paths when you're partitioning before you place. We actually needed a superset of timing constraints across the entire voltage range and feed that back into our synthesis tool. So another way of saying that is we needed multi-corner constraints for a single corner synthesis. So we synthesize at 500, but we set constraints at multiple voltages. The other issue that we needed to address was multi-voltage clocking. So we had a single PLL on this research processor, and we had a clock driving our RLS region, and we had a clock driving our EBB region. What is important is when those varied voltage, obviously the clock arrival times differed, and we have a sequential path between the RLS and EBB regions. So what that meant is we actually needed some, so also there was the level shifters between these regions, which can vary their delay significantly. So what we needed was programmable delay buffers to account for the skew. And we programmed these based on scan, so when we changed our voltage and frequency, we had some pre-simulation numbers that determined what our settings should be for these clocks. We also probed out the clocks and verified in post-silicon that our pre-silicon simulations were correct. So we would scan it in, set the correct skew settings. This methodology gave us about a 1.5 to 2x skew reduction between various voltage combinations. So talking about PV methodology, unlike a typical core where you may have 1 or 2 operating conditions, we have various pairings of operating conditions. So a common example might be the RLS and the EBB running at maximum voltage. It might mean they're running at a moderate voltage. It might mean that the core is at a minima and EBB is comfortably operating, maybe due to variation or various other resiliency issues, or you may have both as low as possible. So how do you have Tango and the synthesis tool actually understand and ensure correct operation at all these corners? So Tango has these intra and interblock skew functions, and what we did was we modified those with a multi-voltage timing analysis. And what we did was we actually created our own voltage mapping and voltage-dependent skew tables and fed those back into the Tango functions. And the way we computed the skew was based on the operating voltage and of sampling end, of launching and then sampling the block. And then we use that to match the entries in the tables. So now I'd like to go over some of our results and summary. So here's a picture of our test bed system as a legacy board. And it's a 32 nanometer high K metal gate technology, 9 metals. The transistor count was about 6 million cores with a total core area of just under 2 square millimeters. There's 168 signals on the package, and it's a 951 pin flip chip BGA. Some interesting things about this is you can see here is a little plexiglass column. On top of that is about a 1 square inch solar cell. And what we did was we had an interposer between the motherboard and our actual package. So we were able to power the chip directly either via an external source, or in this case, we're actually powering it via the solar cell. So here we're booting Windows, and we have a little dancing GIF, and all that is running off this 1 square inch solar cell. So the solar cell is not powering the PLL, it's not powering the I/O, but it's powering the global clock distribution, it's powering the EBBs, and it's powering the core. So some of our test challenges, this is, we get the chip back, we're all excited. There are a lot of challenges, unlike when you, in a research project, you may have a custom board that's 2 weeks old. This was 18-year-old, so there's a lot of variation on all the components. As I mentioned at the top of the talk, the front side bus spec was 3.3 volts. When we were actually probing that, we were seeing anywhere between 2 and like 4.2 volts. So it was a lot of skew in there. And it was important to tune each I/O for every single front side bus pin. We kind of took a shot in the dark by putting a legacy part in there, probing the signals, trying to figure out what it was really trying to drive, and then tuning our I/Os on a per front side bus pin basis. Another issue is as we really drove the voltage down, we were operating below 15 megahertz. Well, the problem is a lot of peripherals fail below 15 megahertz. So we obviously had to drive the entire motherboard at that frequency so it could communicate to the core correctly. So there's a lot of hacking of the various frequency components on the motherboard to enable proper operation. Another issue is unlike modern cores that might have nice micro breakpoints and advanced debug features, we pretty much had BIST. So the ability to start and stop and run specific benchmarks to get meaningful power measurements was fairly degraded. So what we did for our power performance measurement was run BIST. Here's a chart showing our results. You'll note on the far right side at 1.1 volts, we achieved 741 megahertz with a core power of 444 milliwatts. The C9 at this point was 0.45 nanofarads, and as we scale all the way down, we have 0.38 or 380 millivolts for the core, and the EBBs are operating at 650 millivolts. And we got a core Fmax of 10 megahertz at a total core power of 1.5 milliwatt. So this is actually active running a BIST loop. And so this is also demonstrating that we did achieve our wide dynamic range goal. So total power breakdown, you do notice the quadratic nature of the voltage here. And also, Another interesting thing to note is that leakage is still there as we drive the voltage down. At 380 millivolts, we're seeing about a 50% leakage contribution. So just because you pick the right process and you're applying NTV techniques doesn't mean you can ignore leakage. There's still, applying leakage techniques is still important. So it's 3% at the maximum voltage. So now I'd like to discuss the energy per cycle. And this is under a typical skew condition. You can see here that the total energy minima is about 450 millivolts, and the total energy reduction is about 4.5x from our Vmax condition. And what this ends up being is about 135 picojoules per cycle at the energy minima. I'd also like to just highlight the temperature dependencies here. As temperature increases, so does energy. So just because you have an NTV chip doesn't mean you can completely ignore cooling. It is important to still operate under those cool conditions. Here you can see it's about a 25% increase from 5C to 60 degrees C. So here's the same plot that you saw 2 slides ago. This is the energy per cycle under a fast skew condition. Note that the energy minima has changed. We're at 500 millivolts. And please note this is not a different process. This is the same process, just a different skew. So it's important to recognize this as if you're going into a mass manufacturing situation that your energy minima will actually change. So if you're going to tell an application, here's the energy minima, you also need to be aware of what your particular core skew is. So I've described all the good things. Now I'll describe what are the penalties for implementing this technique. So we started with an audit database of the P54C, which was none of the techniques I've described have been implemented, just standard synthesis, 1 volt, and then compare it to our various databases and techniques. So modifying the sequentials, that was upsizing the keepers and creating these clock inverters. Also, this is also taking into account upsizing the actual devices to handle the wide dynamic range. So instead of with the upsize internals, you also may need to upsize all the components of the flip-flop to drive a bigger load. So this is about a 27% area penalty. Pushing the performance at 500 millivolts was a 24% penalty. Pruning all the complex cells was a 10% penalty. We actually ended up using 3 RLS blocks instead of just 1 big block. This actually helped us with our timing convergence significantly, but that cost us 8%. Eliminating all the minimum Z devices was a 5%, and then various other miscellaneous tweaks was 2%. So to summarize, I've demonstrated today the industry's first NTV Intel architecture core with a 380 millivolt vmin, a 1.5 milliwatt total core power, a 293x total power reduction from Vmax to Vmin, and a 4.5x total energy savings. And we've also demonstrated that it has a wide dynamic range. And we have our A0 silicon booting into multiple operating systems, including we have a pared down version of Linux, we have DOS and Windows XP. And I've pretty much said most of that. Looks like my time's up, so I will just leave it here for people to read and go to questions.
So let's thank Greg. We take a few questions. We have one right here.
Hi, I'm Barry Pengerly. Very nice talk. I was wondering if you could say a little bit about how many of these chips you actually manufactured, and then about how many of them worked at any operating point, and then how many of them worked across the range you were targeting.
Certainly. We packaged about 50 of them, and out of that 50, we instantly burned up 2 or 3 due to the motherboard problems that I described earlier, because we just didn't tune our pull downs enough. So out of the remainder, I can think of, there was one that was just acting kind of flaky. Now, this is at the 1 volt operating condition. The real question is how many worked at 380 millivolts. We didn't run all of those there. As you can see, the fast SKUs didn't even, the faster SKUs could get down to that lower voltage, but the slower SKUs couldn't get down to the voltage minima, but they did reach the energy minima.
Over here.
Hi. Could you comment on the the choice of the VT? In your earlier slide, there was a graph showing high VT curve
Yes.
and low VT curve, but it wasn't clear which one you ended up with.
So our goal here was energy minima, not voltage minima. If it were voltage minima, the low VT option would have allowed us to get to a lower voltage. But the goal here was energy. Ultimately, when you're paying your electric bill, you don't care what voltage things are running at. You care about how much energy you burn. So the high VT case was superior for the energy minima.
And one more over here.
Todd Besnick, Omnifidus. What I really care about in the long run is how much energy do I use to get some computation done, and then how dense can I pack that stuff into a room or whatever. Do you have numbers that would give me an idea using?
Are you asking for a benchmark result?
Well, you already said that that's kind of tricky.
So we did run benchmarks, and so we have our legacy 66 megahertz, and I did put that in the backup slides, which I put them in last night.
Awesome.
They scaled, so we scaled both the front side bus and the core linearly with the motherboard. So as you would expect, those benchmark results just scaled linearly. I just caution you by saying I'm not here to present the P54C as the world's greatest low power architecture. So this is simply a platform that we use to demonstrate the techniques. Obviously, a ground up architecture with low power, low energy in mind would be much more superior. And that's why we didn't present the benchmark results. It's just kind of, okay, well.
And those updated slides will be available in a day or two, probably.
Yeah, I think they upload them, yeah.
Okay, thank you very much, Greg.
Yeah,
That's great.
thank you.
So the next talk will be actually somewhat similar in spirit, reducing transistor variability for high performance, low power chips by Rogenmoser. Roger is SuVolta's Senior Vice President, Product Development Engineering. He did his PhD at SuVolta. He did his PhD in EE at ETH Zurich, then went to Intel's CPU group in Santa Clara. He joined SciByte, where he designed a floating point unit from scratch, did an MBA at Santa Clara, left Broadcom for Transmeta, then worked for Novatork and IDT before taking over engineering at SuVolta in 2010. Roger?
Thank you, Forrest. Good morning. I'm here to talk about how variability limits chips and how we can lower power and improve performance by reducing transistor variability. So first I will look at the mobile SoC and circuits and see how they get affected by variability. Then I will actually dive a little bit into transistor physics. I think it's a technology session, so you're going to see a little bit transistors here and see where the variability comes from and what the industry is doing about it, what other technologies, what alternatives are there. I will mostly focus then on the DDC transistor. It's a deeply depleted channel transistor that we developed at SuVolta, and I will show you silicon measurements result. And then apply those results onto the mobile SoC again. So if you look at the mobile SoC, this is a block diagram we came up with. There are many, many different blocks on it, So you have a high-frequency CPU. You have a GPU that runs a little bit of lower frequency, but has many different cores. Then you have a bunch of other blocks on it to do other things, memory interface. You also like to have the modem on the chip, so you can integrate anything on the same die. And the problem with integrating everything on the same die is essentially you have one transistor to do that needs to be used for all these different blocks, for these different power modes. And so far, we're pretty much using only the multi-VT capability of the transistors. So in these blocks, you know, people have used dynamic voltage and frequency scaling. And I think last week, and some executives said, the voltage scaling is dead. And Gregory just showed you it's not dead, but it's quite difficult to deal with it, work with it. The reason for that is you cannot raise the voltage anymore. You have reliability concerns. You also have power density concerns. It gets too hot on the local spot. Lowering is difficult too because the performance drop-off is too steep, so you don't really get a good range anymore. Some people do just the frequency scaling, but frequency scaling has a drawback that your leakage power is not affected, it stays high. And so the design teams pretty much went to the run-to-hold technique. You turn the block on, you run as fast as you can, and turn it off again. And that beats voltage scaling these days. The second problem is that SRAM memories don't have a good voltage scaling. So the Vmin, the minimum operating voltage of SRAMs, is going up and up and up, and 28 nanometer, 20 nanometer, the outlook is, it's pretty much there at the nominal voltage. So design teams have moved to a new technique where they add a second power rail for the memories. So you have a power rail for the logic, a power rail for the memories. In the CPU, that works quite well because you have your big I cache and D cache and just hook that up to the separate power rail, and then you can do voltage scaling still a little bit on the logic. Now, if you look back at the GPU, the GPU has hundreds, if not thousands, of small memories. So hooking up all these little memories with a second power rail is quite tedious, and not everybody is willing to do that. So when we talk about variability, transistor variability, there is two main sources for transistor variability. One is the global, systematic manufacturing variation. The other one is the local variation. So the manufacturing variation is pretty much all the chips, all the transistors on the same wafer get affected the same way. So the wafer, for example, might have longer channel lengths. So all transistors get slower. Or the implant dose, you know, the machine there is a little bit off tune and gets a little bit less implant. So all the transistors get a little bit faster. Everything is faster, but also leakier. So, but it will affect everything the same way. So everything shifts the same way. And this is also shown in the manufacturing distribution. You see on the top right graph, you know. So then you might end up with some parts that are too slow and some parts that are too hot. The new problem, or the newer problem is, and it really became a problem only in the recent year for designers, is random variation. Random variation is this thing where you have two transistors sitting next to each other, and their VT varies a lot. The reason for that is that the transistors in 65, 40, 28, 20 are so small that the number of dopants, the dopants that set the VT of the transistors, are so small that you have statistical fluctuations. And so instead of the 200 dopants that you plan to have, you have a distribution, let's say. And this is actually then results in a varying VT, as you see on the right-hand, on the second graph there. And this impacts everything: speed, leakage, SRAM, analog. So it's pretty clear what to do about it. You have to get these dopants out of the channel. And if you remove the dopants out of the channel, you remove the main source of random variability, random dopant fluctuation. So we have to figure out now what silicon roadmap is the right roadmap that deals with manufacturing variation and random variation. So here are the alternatives that people are using or promising. The most publicized is the FinFET, or as Intel calls it, Tri-Gate. It has a very good channel control and a high drive current. The challenges with it is manufacturing. Only Intel is manufacturing it these days. The cost of it, it's a 3D structure. And when we build chips, we have a lot of circuit IP that we reuse and use, so you have to move all your circuit IP there. That's an additional cost. The textbook FinFET is an undoped channel. However, what we learned from recent presentation in Intel is actually Intel had to dope the fin again. So when you dope the fin again to get multiple VTs for your transistors, for your designers, you lose the random variability benefit again. The second alternative is fully depleted SOI. It's pretty much a very, very thin channel over SOI. It's undoped. It shows off the undoped channel benefits. It has a good body effect and multi-VT capability. However, companies are really nervous about using FD-SOI because the supply chain is quite restricted. The third technology is a deeply depleted channel transistor that we developed at SuVolta. It's an extension of CMOS, has an undoped channel, and a good body effect, and multi-VT capability. So here is a graph of the DDC transistor. Essentially, the channel consists of 3 different layers: an undoped layer, a VT setting region, and a screening region. So this is the physics slide, so bear with me. The way we built this thing is quite simple. We take the wafer, we do the implants first for the screening layer, we do the implant for the VT region, and then we grow a pure silicon layer on top of it, tens of nanometers. That will build our channel. So we have an undoped channel. The undoped channel really is, with the dopants out, gives you the lower variability, the lower random variability. And I will show you it's good for SRAMs, for leakage, for speed. It also gives you tighter corners. And it will help in analog design. An undoped channel, any undoped channel, has higher mobility, so your chip will be faster. The VT setting layer is really what it does. We dope it differently and get different VT transistors. And finally, we have the screening region that kind of closes up the whole design, the depletion region of the transistor, but it gives you a good body control. And the body control really is another tuner, a lever, where you can actually tune the VT of the transistor and adjust the performance of it. So here is my random variability graph again, or the VT distribution. This is a large number of transistors. When we look at leakage, leakage is exponentially dependent on the VT. So the graph on the right gives you the power curve, and you see the main power comes from the lower VT transistor, so the curve is shifted to the left. Now what we can do, when we cut the random variability, we cut the sigma VT of it. We cut the sigma VT here from 60 millivolt. That's a typical SRAM transistor, to 30 millivolt. We also cut the leakage, the high leaky devices away, and our power, just by using a lower variability transistor, goes down by 3x. Here is an overlay of actual transistor measurements. This is SRAM transistor fabricated in 65 nanometer, and you see the distribution here, which I fitted to my model, and you see that the baseline matches my model. The DDC transistor actually has a tighter distribution. We actually achieved more than 50% random variability reduction. And as it turns out, that SRAM had about 5 times lower leakage. This VT distribution has another side, another tail, the high VT tail, and the high VT tail affects speed. So these are, you have to think of it in a big place in route design. You have multiple critical paths. They're all very similar. Depending on which run you're doing, different ones are limiting your speed. We can model this with ring oscillators that we just fabricate on the same wafer, on the same die, and measure the ring oscillators. So here is a measurement of around 30 ring oscillators. And you see, nominally it should be 400 picoseconds. However, due to random variability, I get a distribution. Now, if I build the same ring oscillators in DDC, I get two things. One is a speed up, and the second thing is a tighter distribution. So I don't just get the benefit of the speed up from the higher mobility, I also get the benefit of the tighter distribution. So I'm at hot chips here, so most of you probably are speed junkies and want to go for faster transistors, so you can just use this. The other way, though, is, and that's an application that is interesting for the mobile folks, is to lower VDD. So we lower now VDD until our distribution matches the baseline distribution. Lowering VDD has a huge impact on power because it's a square law here. Some circuits that are affected with random variability are SRAMs. And SRAMs, you know, you have 6 transistors in your SRAM cell that need to be perfectly balanced. However, they're the smallest transistors on the chip. So small transistors have the biggest random mismatch. They're the worst affected. So that's essentially why you have to raise the voltage to make this thing work in modern technologies. What we did in the 65 nanometer technology, we improved the Vmin from around 0.75 volts to around 0.4 volts. And you see in the butterfly curves down to 0.4 volts, we have very good noise margins. It also affects analog circuits where matching is key. And analog designers just went out of the way to remove random variability. They just made their transistors huge. So if you have better random variability, you can now make these transistors smaller again. If you have smaller transistors, you actually have less capacitance. You can speed up. You get higher performance analog circuits. And you also get an area saving on your analog transistors. On top of it, what we've seen with the undoped channel is you have a higher R-out. R-out is something that analog designers use to make better amplifiers, and we get like 4x higher gain amplifiers. So far, I've talked about random variability. Now let's look at manufacturing systematic variability, what we can do about it. The key here is really to use body biasing to fix the systematic variation. So same graph again as before. You have slow parts, you have hot parts, and what you do is you apply a forward bias to the slow parts, and you apply a reverse bias, make these fast hot parts slower, and you get a tighter distribution, and you can sell everything of your manufacturing distribution. Body bias can also be used for other things. You know, you can optimize the power mode, the power on every different power mode. You can improve standby. You can improve power gating. Body biasing is not free. Like the random variability improvement you get from the fab. Body biasing, you have to build for it. You have to implement it in your design. So people have done it, but they stopped doing it because the body factor became very small, and the benefit was not much, there was not much ROI in doing it. So in DDC, we actually see that we have about 2 to 4x larger body factor, and it's well worth using this technology. If you're planning to use FinFETs, there is no body effect in FinFETs, and this technology won't work for you. This technique won't work for you. Here is some measurements, some silicon measurements from ring oscillators. So we have manufactured a bunch of ring oscillators. We have manufactured corners, slow, TT, FF. And we have the baseline rings in red and the DDC rings in green. Baseline runs at 1.2 volt, DDC runs at 0.9 volt. What you can see in this graph is the DDC rings are to the right, meaning they're faster, and they're down, meaning they're lower power for every corner. If you're looking at the product, we're really interested in the baseline speed, the SS speed. That kind of defines what the speed is for our parts. So what we're going to do to compare the power here, we normalize the power for the fast pass and typical rings. And then we apply body bias on the DDC rings. And what you can see here, we achieved about 50% power for the same performance. So in this example, I used manufactured corners. This means we tuned the tools so they're having longer channels, shorter channels, more implant, less implant. So we actively did it. However, when we actually look at real corners, that means we're running multiple wafers, we see that DDC has a tighter corners. You see that on the graph here where we have the baseline in blue and DDC in red, and it's the VT distributions across multiple wafers, multiple transistors. So you see the manufacturing variation, but you also see the random variation in this graph. It's combined. And if you look at the 3 sigma, the outer ring of the DDC distribution, you see this about the same size as a 2 sigma of the baseline distribution. That means we have about a 1 sigma better corners. 1 sigma better corners means in design, I don't have to do that much over design to hit fast and hold time and setup time. I do less over design. I'm going to get done faster. I might actually have a smaller design. I might tape out earlier, and I have a quicker time to market and can sell my chip earlier, quicker. So I've showed you the example at 0.9 volts, so let's push voltages. Let's see what we can do at different voltages. This is the same rings again, you know, with the corners and then the normalized frequency for the baseline. And there is room to the left, so there is where we put in our DDC at 0.6 volts. So at 0.6 volts, we still achieve half the frequency, but at 1/6 of the power. If I think back about my mobile SoC, GPUs have lots of cores, so this gives me kind of the idea, oh, maybe I should put in more cores and run them at lower power, a lower voltage and get the lower power, because I can put down 2 blocks, run them at 0.6 volts, and the combined power is 1/3. So this is even better than running at a 0.9 volt and at the same performance. It costs me area, of course, so you have to deal with that. You've seen in Gregory's talk that when you go to lower voltages, temperature becomes very critical. And temperature becomes critical because it affects the VT of the transistors. So at 0.6 volts, you have only very little gate overdrive, we call it. It's the difference between the VT and your VDD. And if the temperature fluctuates, the parts get faster or slower, or it makes your design very complicated. So you have to deal with, in the design phase, with all these different corners. The way out here is body biasing again, because we can just compensate for temperature variation. This makes that we have a good design window, and we avoid over-design. Again, it's hot chips, so I hope by now you agree with me that we can do lower power with DDC. And now I want to look at how much faster we can go with DDC. And for that, we have the same rings again, but this time, instead of running it at 0.9 volt or 0.6 volts, we just run it at 1.2 volt, like the baseline, like the original transistors. And what we see here, we achieve over 50% speed up. Power goes up, but it's still 50% faster. You don't get it any other way. If I have a CPU on my mobile SoC, this is a perfect turbo mode. I ramp it up, run it faster, and come back down. And we actually have a reasonable dynamic voltage and frequency scaling range, as you can see in the table. We go from 0.6 volt to 1.2 volt. Speed goes from 0.5 to 1.5. So the numbers I've showed you so far have been 65 nanometer silicon data, and this is an outlook to 28 nanometer. We have run initial wafers and have transistors extracted, built SPICE models out of it, so that's kind of called silicon calibrated SPICE. And we simulated the ring oscillator here, and what you can see is we achieve about the same performance at 0.75 volt as the baseline at 0.9 volt. Now this corresponds to about a 30% power savings, or again, if you want to go faster, you can also go vertical, stay at 0.9 volt, and it gives you about a 25% speed up. Body bias still works, and you can use it to improve the speed, the performance of your part even more. Let's go back to the mobile SoC. How would I use DDC in the mobile SoC? First, the CPU. When it all comes back down to its single-thread performance, you need to check up the single-thread performance now and then, and the only way to do it is if you have a good turbo mode. So push the voltage up, go to 1.2 volt or go to 0.9 volt in a 28 nanometer technology, and go back down, do voltage scaling. So the voltage scaling then becomes, rather than DVFS, we add body biasing, so it becomes DVBFS. If I look at the GPUs have smaller transistors, have big paths, but since we have the reduction in random variability, we have also less delay variability in the GPUs. We can use that. Then we can also increase the parallelism, plonk down more units, and run them at lower voltages. The same goes for the other blocks. So you can find an optimal voltage and an optimal VT for those blocks. You don't need to run everything at the same voltage just because it doesn't work at lower voltages anymore. For the whole chip, we want to do body biasing to fix the manufacturing distribution. And we can actually also integrate analog because our analog function is quite good. Analog performance is quite good. So we've seen in this talk, variability is a big limiter to chips. DDC reduces random variability thanks to the undoped channel. DDC has a strong body effect that we can use to fix manufacturing variation and also temperature variation. It gives a performance kicker from 90 nanometer to 20 nanometer and beyond. It's pretty much a straightforward integration into existing nodes because it's compatible with the bulk planar CMOS. So your IP, it's an easy conversion to DDC. It's pretty much just a tuning. It works with the CAD flows that we have. There is nothing new you need to do. We also get the low power tools back from DDC, so we can do large range DVFS. We have body biasing, and low voltage operation is actually possible. To do this, that's not going to be easy. It needs a combined effort because some of these things affect architecture. You need to design for it, and you want to have the optimized technology. This concludes my talk. Thank you very much for your attention.
Well, thank you, Roger. Some questions? Looks like we have a couple over here. One.
David Cantor. So one of the things you talked about as being a substantial advantage is the adaptive body bias. Now, that's something you can also do on fully depleted SOI. Could you quantitatively contrast the body bias effect for, say, fully depleted SOI versus your deeply depleted transistors?
Yeah, fully depleted SOI. I mean, if somebody from ST will probably give you better answer there. But the main difference is you have a silicon isolation between the channel and the body, and so you can jack up the voltage much higher. That's what they claim in their papers. I don't know how you do it in practice. So the second problem, though, with fully depleted SOI is you have no way to make multi-VT transistors. So you have to somehow use body biasing to make different VT regions. So.
All right, but how much of a difference in body bias effect do you think you get between the two? Like a factor of 2 or 50% or?
So what we did in 65, I can tell you that, is like we use like up to half a volt back bias. So So, and that gives us about a 200 millivolt VT tuning, which is well within a VT level up and down. So.
Thank you.
Next. Over here on this side.
Yes, a question on the body biasing again. Is there, have you quantified the impact? Is there an area impact or overhead involved with adding this extra control, I guess?
Yeah, that's a common question about the body biasing. So I don't have it here in my presentation, and we just actually we just designed an ARM SoC, and it's in manufacturing. And what we see actually, there is no area overhead. Okay, you need the charge pumps and all these circuits, so you need to find a place it, but your logic block has no area overhead. Actually, what we've seen is your logic block becomes smaller because pulling in the corners reduces over design, and you get a little area saving there. So right. We're gonna show these results whenever we measure the silicon. So
okay, thank you.
Over here.
Don Draper from Oracle. First question is, you're using your VT layer, which has different amounts of doping in it to compare to vary the threshold, and so the implication, I think, is that the variation in that doping, that VT doped layer, is less than the traditional way of varying VT. So why is that different?
So the current flows in the undoped layer. So that's where your channel is. So that's the dopants are out of it. The way you have to think about the VT layer is really it's the potential that puts it in the channel. So it's a very thin, like tens of nanometer silicon layer, and the VT layer is actually comparably high doped compared to what you would have in a baseline device. So there is many more dopant atoms in it than in a regular baseline device. So,
thank you.
Over here.
Yeah, Nathan Brookwood from Inside 64. Looking at the difference between the benefits of your approach at 65 nanometer and the 28 nanometer performance gains that you're suggesting, you went from basically a factor of 2 improvement in either performance or power reduction to a factor of 1/4 in terms of power reduction or performance improvement. So it looks like as the geometries get smaller, the benefits of your approach get less. Have you looked at this at, say, 20 nanometer to see how that would play out? Or is there something in the approach that's going to make it less and less interesting as geometries shrink?
Yeah, we're working on 20 nanometers. We see similar benefits like 28 nanometers. But you're right, there is less. We're getting less, moving to more advanced nodes. However, in 65, we're about to run products, so it's much more mature than the initial transistor results that we get in 28, and we expect to improve upon that. But I want to show you what I got and not what I think we're going to get.
So was it 28 nanometer? Was that modeled, or is that based on any real?
That's based on transistors, so initial transistors. Yeah.
Okay, thank you.
One more over here.
Mm-hmm. He's Ando from MyCom. My question is that you said that the VT setting layer is highly doped so that the variation is smaller. And may I ask that, say, which is larger variation factor? One is in VT setting layer doping or the thickness of the depletion layer?
So,
which is larger component of your VT variation?
So it's a good question. So I don't know the exact answer. So the thickness of the undoped layer actually affects the VT very, very much. So, however, these modern epitaxy tools, and they only came out the last 5-10 years, that's why nobody did it 10 years ago, is you can pretty much control on an atomic level across a wafer how thick your silicon layer is. And 1-2 nanometers doesn't really change the VT that much, and that's already 10 layers of atoms. So.
Thank you very much.
And last one over here.
Ted Williams, Microsoft Silicon. So one of the benefits of controlling VT by doping, as traditionally done, is that I can tune my paths on a transistor by transistor basis by choosing what VT of high, medium, or low VT. You're saying body bias is the golden answer here to control everything, but what granularity are you envisioning, both in space, by gate, by row, by block, and by voltage? How many different voltage levels of body biasing are you envisioning, and how many different charge pumps, and how are you going to distribute that?
No, so you still have multi-VTs. So I have high VT, I have standard VT, and low VT in my design. So that you can still choose, my critical path in the CPU is going to be low VT, and whatever next to it can be high VT. That still works. You can use this design approach. So then the body biasing you use on a block, you cannot do it on a per transistor basis because you need to isolate, and the area overhead would be way too big. So you do it on a bigger block basis. But you still have multi-VT transistors, so you can still do what you did in your design. And whatever is critical path, I use low VT. Whatever else, I make high VT. That still works.
Can you comment about granularity of body bias? How many different biases?
It's really, there is different ways to do it, but we typically do have two body biases, one for SRAMs and one for the logic, and that's it. So that's in a simple design. In the mobile SoC design, I probably would invest a little bit more because you can get more out of it and do more regions. But you want to keep it up to a bigger block level because you need a charge pump, you need a controller, and you need to isolate that thing. So.
Thank you.
Okay, Roger, we'll be outside at the break. We're a little late for our break, but let's try to be back here at 10:45. Thank you, Roger.